Right. In this video, we are going to look at the FRQs from the practice set last time. Part A of this first one is saying use the data in the table to approximate the rate. So they want us to give them a rate in hundreds of entries per hour at which entries were being deposited at time equals 6. Show the computations that led to your answer. All right, so the main information that we're given here is this table, right? And where T is in hours and E of T is in hundreds of entries of people to the zoo after that many hours, right? So at time 0, there were zero people at the zoo. At time 2, there were 4 people at the zoo, or 400 people at the zoo. At time 5, after 5 hours of being open, there were 1,300 people at the zoo. At time 7, there were 2,100 people at the zoo. At time 8, there were 2,300 people at the zoo. And we're being asked to find the rate of change, how many people are being added per hour to the zoo at T equals 6. And notice how T equals 6 is missing. Well, to get a good estimate of it, which is what it's asking, we just need to find the rate of change between 5 and 7, right? So you can just kind of look at this and be like, well, 2 hours went by and 800 people were added, right? 800 people in 2 hours is 400 people per hour, right? But the official formula for doing it is the slope of a secant line, right? And in this case, it's f of 7 minus f of 5 over 7 minus 5, which is 21 minus 13 over 2, which is that calculation we already did, which is 8 over 2, which is 4. And then you have to realize it's 400 people, entries per hour. Right, and then we also showed the computations that led to our answer right there, right? Okay, part B says use a trapezoidal sum with the 4 subintervals given by the table to approximate the value of 1/8 integral of 0 to 8 e of t using correct units. Explain the meaning of 1/8 integral 0 to 8 in terms of the context number of entries. All right, so the first thing we need to do is do this trapezoidal approximation. Remember this, the integral symbol represents area under the curve. And so we're going to use trapezoids to approximate the areas under the curve, right? So what I always find extremely helpful is to create a graph. It doesn't have to be a nice graph, but a graph is good. There's 2, 4, 5. Let's put 13 here. It doesn't even have to be drawn to scale. 7, 21, and 8, 23, right? And what we're going to do is it said divide it into 4 subintervals, right? So using the chart, right? So if you just draw the subintervals based on the numbers that are given, you get this. And then it said use trapezoids, so that means we are connecting those like that. And there are 4 trapezoids here. Technically, this small one here is a triangle, but maybe you didn't know this. Triangles are a special type of trapezoid, where one of the heights is 0, in which case height 1 plus height 2 is just height 2 or something divided by 2 times the base, which is the formula for a triangle, right? So we're going to estimate this. We're going to write 1 over 8 is approximately 1/8. That's just that same 1/8 that's right there, times the area of this first trapezoid is height 1, which is 0, right? 0 plus height 2, which is the y coordinate at 2, which is 4, times base over 2. The base here is 2 over 2. That's the first trapezoid, which is a triangle, right? Next one is height 1, which is 4, plus height 2, which is here, 13, times base, which is 3 over 2. That's the second one. Plus the third one, height 1 is that 13, plus height 2 is the 21, right, this guy here, times base, which is 2 over 2. And then the third one is height 1, which is 21, plus height 2, which is 23, times base, which is 1 over 2. And this is a calculator problem, so we can just do all this on the calculator. Just go to our calculator and just do 1/8 times these parentheses. 0 plus 4 is 4. 4 times 1, right? 2 over 2 is 1. Plus 4 plus 13 is 17, times 3/2 is 1.5. Plus 13 plus 21 is 44 times 1. Plus 21 plus 23 is 44 times 1/2 is 22. And close those parentheses. And it looks like we get 11.9375. And then the hard part here is we need to explain the meaning and give in terms of the number of entries, right? So this is one of those formulas that we were looking at in class. It's the average value formula. So we took the average value of E, which is the number of people in the zoo, the number of people who entered the zoo, right? So this is, the meaning of it is hundreds, 11.9375 hundreds, or we could write 1193, about that many people on average in the zoo from t equals 8, 0 to 8. All right, it's the average number of people, average number of entries. All right. I'm sorry, I misread this. The thing is, the entries are for a contest, right? So it's not people, it's like entries. It's the average number of entries from t equals 0 to t equals 8. Next one, volunteers begin to process the entries. The process entries, they process entries at a rate modeled by P of t, right? So this is a rate function of how many entries are being taken out, right? So, and this is for 8 to 12, right after the zoo closes. According to the model, how many entries had not been processed by midnight, right? So we have to think is like, well, we're going to start processing entries, right? So this is going to be we want to know the number of entries at midnight, and how we get that is the number that we started with, right? And then we subtract the number that get processed, right? So the entries at midnight is what we want. How much do we started with? Like, how many entries do we have at 8, right, when we're going to start processing them? How many total entries do we get throughout the day? Well, we got 23 2,300 entries, right? And then we're going to subtract. Well, if P of t is the rate, then if we integrate P of t from 8 to 12, it will tell us the total. It will tell us the total amount of entries processed from 8 to midnight, right? So this is a calculator problem. We're just going to do math 9. Now we're going to go from 8 to 12, and we're going to do this P of t function. And we get 16. So really, I guess what I should have done here is just put 23. So it's going to be 2300 minus 1600, and that's going to give us a total of 700 entries remain, right, or are unprocessed. All right, and then the next one is, according to the model from part C, at what time were the entries being processed most quickly? This is a tricky one. So when are they being processed most quickly? What I find helpful is imagine we have this graph, time versus process speed, which is that P of t that they gave us, right? And let's pretend P of t looks something like this, right? And these are just different times. Where would they be processing them the quickest according to this graph, right? So like, I don't know, just assign some numbers. 1 entry per hour, 2 entries per hour, 3, and this is like wrong, but just go with it. Where like, so like think like right here at time 0, they're processing them at 1 entry per hour. At here, right, they're 2 entries per hour. Here, they're 3 entries per hour. There, they're 4 entries per hour, 5 entries per hour, or 4 entries per hour, 4 point something entries per hour, right? So like, can you see that like right here is the fastest processing speed, right? So since we actually have the function, we can actually, and a graph, and we're allowed a graphing calculator, we can actually just graph this thing. I should have just put it in my calculator earlier, since I have to enter it again. And the hard part that you're going to find is that your window is not going to be right, because this has like a really large window. But let's try zoom fit and see what that does. And we're actually interested in 8 to 12. So we could just go from, let's just go from 7 to 13. And we're gonna have to change that again because it's not liking this. Yeah, we need to show more up here. Let's show up to, we don't need to show that. All right, there it is. So remember, we stop at 12, which is right here. And the question becomes where, and this is the rate function, right? So we're basically want to know where's the maximum rate, which is either occurring over here at 9 hours or it's occurring at the end point here at 12 hours. And so one way you can do this is remember how we maximize a function, right? Like if I give you this function minus, come on, minus 976. If I give you this function and say to maximize it, like do you remember the maximizing process? You find the derivative, right? Because we're trying to find the critical values where the slope is 0. So you would get and then you'd set it equal to 0. And then you would try to factor this, which is, you know, these are kind of big numbers, but remember we're trying to get these things to multiply to give us 298, had to give us 60. We already looked at the graph, so here's a hint. One of them is going to be t minus 7 because there's an x-intercept at 7, and the other one is probably going to be plus something. So they're, well, no, they both have to be minus. And so we have to figure out what 298 divided by 7 is, so that doesn't work either. Just a second. Sorry, it's not, that's not an x, that x-intercept's not 7, it's 8, right? So if we do 298 divided by 8, you only get 37.25, which also doesn't really work. Okay, well, I was going to show you, I was going to take you through the steps of how to do this algebraically, but it turns out that this is not, it's not factorable. And so we actually can't do it. Well, we could do it algebraically. You'd get to like the quadratic formula or something like that. But like if you get to a point on the AP exam where you're being asked to use a quadratic formula, you should probably try something else. So let's look at our calculator real quick. The idea of what we were trying to do algebraically is the maximum values will occur at endpoints and critical points. And so you can see that on this graph, right? Our endpoints start at 8 and end at 12. So they'd be 8 here, which the rate at 8 is 0, or 12, which the rate at 12 is somewhere up here. We could look up, like, we can actually find that out. What is that? Second trace. Let's get a value. What is the value when x is 12? Y is 8, right? So we're processing at 800. But it also happens at critical values, which you can see the critical values up here at this relative max. And you can use your calculator to find that as well. So let's do our table of values, right? So if we did t and p of t, then at 8 it was 0. At 12 it was 8, and then we have to find that critical value as well, which is going to be trace. It's a maximum. Oops. And so we got to go left bound of that little maximum. Remember, we don't care about that minimum one there. We only care about the max one that's way over here. So we got to go left of that, and then we got to go right of the max, and then guess. And it's going to show us at x equals 9, y is 5. 9 point something. And so then we ask, well, which is the fastest rate? These are the only places the fastest rates could have occurred, and it turns out that the fastest rate was at midnight. So maybe they were really trying their hardest to finish the ballots or something like that, right? So the answer to that one would be the entries were being processed the most quickly at t equals 12. All right, let's move on to this next one, and then move this guy down so it's not in our way. All right, so now we're going to do this guy. This one's talking about a ride of some sort where you have a line. There's some really important information up here. There are 700 people in line when it begins operation. Once it begins operating, the ride accepts passengers until it closes, and while there is a line, people will leave the line because they're getting on the ride, but they leave the line at a rate of 800 people per hour. And then this graph over here this is R of t. It shows us the rate at which people arrive at the ride throughout the day, where time is measured in hours. So remember, just think about it. Like this problem requires a lot of thinking, right? Like think about this: the rate of change of the ride, of the length of the line, is going to have to do with how many people come into line, how many people get in line, minus how many people leave the line, right? And this is given to us, this piece is R of t, which is the graph, right? And then the leaving the line piece is 800 people per hour, right? So the first thing we want to know for part A is how many people arrive at the ride between t equals 3 and t equals 0, right? So this is only asking about people who are arriving at the line, which is this t part, right? So basically, if we want to know the total number of people that arrive at the line, then we have to integrate, we have to add up the total number of people of R of t from 0 to 3. So we're basically finding this area, right? That's the integral from 0 to 3 is the area under the curve from 0 to 3, but it also tells us the net change, right? How many people will have gotten into line. And so you can break this up however you want. I like to see it as that triangle right there, and then this triangle right there, and then the rest are, solid boxes. So this has 1, 1, and then these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So a total of 16 boxes, but be careful, each box is 200, right? It's 1 times 2, so each box is 200 people. So we have 16 times 200, which is 3,200, and that's how many people arrive from t equals 0 to t equals 3. So many people arrive in line from t equals 0 to t equals 3. Next one is the number of people waiting in line, waiting to go in on the ride, increasing or decreasing between t equals 2 and t equals 3? Right, so now we're looking at, is our line getting longer or shorter, right, between t equals 2 and t equals 3. So look at our rate in, right? Like it was 1200, and between the hours of 2 and 3 it was 1200, and it went down to 800 at exactly 3 seconds, right? So our rate in is somewhere between, our rate in is between 800 and 1200. Our rate out is always what? It's always 800. So think about it. The rate in has to be somewhere between that. The rate out has to be somewhere, has to be 800. So are more people getting in line or more people leaving line? And the answer you should be seeing is, this is not minus, this is 2. The answer you should be saying is, well, more people are getting into line, right? 8 to 1200 people are getting in line, whereas only 800 people are leaving. So the line should be increasing because more people are getting in line. All right, next one is, at what time t is the line for the ride the longest? How many people are in the line at that time? Justify your answer. To show you how this goes, I'm going to go ahead and just make a table of values, and you can totally do this without doing this, but so it's going to be time and then number of people in line, right? So time equals 0, they tell us there are 700 people, right? They told us that up there. At time equals 1, How many people did we add? Well, that's the area under this first yellow piece, right? That's how many people we added in the first hour, which is 1, 2, 3, 4, 5, and a little bit, which I don't really know what that little bit is. So let's go ahead and go to 2. So this we can actually calculate the exact area of. It's going to be 2, 4, 6, 8, 10, 11. And remember, each box is worth 12. So we added, sorry, each box is worth 200. So this is, we added 2,200 people. So it's 700 plus 2,200 people. There are 2,900 people after not 1 but 2 hours. And then we could do after 3 hours, right? We're going to add some more people. Actually, I'm sorry, that was dumb. 29. To get this, we're doing 700 plus 2,900 people got on, but 800 times 2 hours got off, right? So it's really 700 plus 2,900 minus 1,600 because those people are getting off. So it's actually 700 plus 1,300 is 2,000. Sorry. And then 3, we're adding all these people, which is another 1, 2, 3, 4, 5 times 2, another 1,000 people. So to get here, we're adding 1,000 people, but we're subtracting 800 people in that 1 hour, right? So we add another 200, so it should be 2,200, right? And then we could keep going. At 4, we're adding all these people, right, in the green, which is 1, 2, 3 boxes, so 600. So here we're adding 600. So we're going to add 600, but we're also going to subtract 800. So we lost 200 there, so we're back to 22,000, right, at time 4. How about time 5? We're going to add, now look, from time 5 to 6, we're going to add the same amount, right? So we're going to add 1, 2, 3, 4 boxes. So we're going to go up to 6 on this one. We added 4 boxes, which is 800. We also subtracted 800 times 2 hours because we did 2 hour interval there. So actually lost 800 people there from our line. So we're down to 1,200 now. And then the last one we'll go to is 8. All these ones, which is 2 boxes, so 400 people. We gained 400, but we lost, remember, 800 times 2 hours. So we lost 1,600 people, so we're actually losing 1,200 people, and now there's nobody in line at that point, right? So when was the line the longest? Well, the line was the longest here at t equals 3. How could we have done that with all that work? Well, it's helpful if you can think about what losing 800 people looks like, right? What it is since it's a constant function, it's just this line right here at 800. That's the rate at which you lose people, constant 800. And if you notice, before t equals 3, we are adding a bunch of people, right? There's way more people getting on than getting off. But then after t equals 3, our rated people getting out of line is higher than our rated people getting in line, and so our line must be getting shorter. And so the point where it's the longest is where these two things cross, right? Where the people getting in line dips below the people getting out of line, which happens at t equals 3, right? And you can explain all that stuff that I just explained. All right, next one. Last one. The function g is defined and differentiable on the interval -7 to 5, including the endpoints, right? That's what those little brackets mean. It satisfies the condition that g of 0 is 5. That's very important. The graph of y equals g prime of x, the derivative of g, consists of a semicircle, right? They're saying this is a semicircle, and 3 line segments, right? 1, 2, 3 line segments, as shown in the figure above. Find g of 3 and g of -2. So they're asking me to find like a new position, right? So part A, we're just going to do, well, g of 3 is going to equal the point I know, which is g of 0, plus the integral from 0 to 3 of g prime, right? This is that new position thing that the formula thing that we had. And so, g of 3 equals g of 0 was 5 plus the integral from 0 to 3 is the area under the curve. So we're just trying to find, well, what's the area under the curve here, right? This one's a triangle, 1 times 3, so it's going to be 3 halves. This one's a quarter circle, which is pi r squared over 4. R in this case is 2, so pi times 4 squared over 4. This is going to be pi. And so g of 3 is 5 plus 5 pi. G of negative 2, same idea. We're going to do g of 0 plus from 0 to negative 2 of g prime of x. G of 0 is still 5. Here I got to go to 0 to negative 2, so I got to go this direction. We're going backwards, which is something you could just set up automatically. Is go ahead and just change that to a negative, and then calculate it. So what's the area from negative 2 to 0? Well, that's going to be that little green quarter circle, which is pi. So it's 5 minus pi in that case. Oh, I messed this other one up, right? I forgot the 3 halves. This should also have pi plus 3 halves, right? Because that old triangle. So yeah, don't miss that one on that one. Next one, B, find the x-coordinate of each points of inflection. Remember, a point of inflection is where the slope changes from increasing to decreasing or decreasing to increasing, right? So we're looking at this graph and we're asking, when does the slope of g of x, right? When does the slope change from increasing to decreasing or decreasing to increasing, right? And we're looking at g prime, which is the slope of g of x, right? So we can just follow this up and be like, okay, increasing, right, from negative 7 here, increasing, 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 right, because it's going up, and then it's still increasing, 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 and then it stops, and now it's decreasing, decreasing, decreasing. So the slopes started or changed from increasing to decreasing at x equals 0, right? G prime changed from increasing to decreasing. Any other ones? Let's keep looking. Let's keep going. Decreasing, 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 increasing, 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 increasing. So notice how it changed again, right there. So that's x equals, the first one's supposed to be x equals 0. X equals 2 also works. G prime changed from decreasing to increasing. And then we keep going. It was increasing, 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 and then decreasing. So also x equals 3. Because it changed from increasing to decreasing, right? And the last one's part C, which is a little bit funky. They're giving us this h of x, which is g of x minus 1/2 x squared. They want the x coordinate of each critical point of h, and classify it as a relative min, max, neither, right? So in order to find critical points, remember the steps. We take the derivative, we set it equal to 0, and we find if it's positive, negative on each side, right? So the first thing we need to do is take the derivative. Derivative of h is h prime. That's the left side. Derivative of the right side. Derivative of g is g prime. And the derivative of negative 1/2 x squared is negative 2/2, which is 1. So negative x. And we want to know, when does this equal 0? We can also go ahead and try to solve. Basically, it's when does g prime of x equals x? And it is kind of like funky unless you just try stuff, right? Does g prime, and let's just start on the left, does g prime of negative 7 equal negative 7, right? We're replacing these x's with some x values. So we'll go up to the graph. Is g prime of negative 7 negative 7? No, it's negative 1, so that doesn't work. All right, we could buy is g prime of negative 6 equal to negative 6? Well, here's g prime of negative 6. Is it negative 6? No. Is g prime of negative 5 equal to negative 5? No. Negative 4 equal to negative 4? No. Negative 3? No. Negative 2? Is g prime of negative 2 equal to negative 2? No. It's equal to 0. How about here? Is g prime of 0 equal to 0? No. It's equal to 2. Is g prime of 1 equal to 1? No. It's somewhere up here. Is g prime of 2 equal to 2? No. G prime of 2 is 0. Is g prime of 3 equal to 3? Yes, it is. Oh my goodness, right? There it is. So the answer that actually is true here is when g prime of 3 will equal 3. So this is so x equals 3 is a critical value of h of x. And then we need to determine if it's a relative min, relative max, or neither. The idea is we need to put 3 there and then check over here, right? So let's choose like 2, and remember h prime of x is g prime of x minus x. So if I plug in 2, I get g prime of 2 minus 2. Is that positive or negative, right? So g prime of 2 is 0 minus 2 is negative. So this is negative, it's going down. And then we plug in a 4. G prime of 4 is, 4 may not be the best one. Let's do 5. G prime of 5 is negative 1. Minus 2 is also negative. So it's neither a max or a min. There is neither max or min at x equals 3. All right, and that's how that goes. It's all of them. Sorry, it's so long.